Good evening, everyone. Welcome back in this webinar series on nonlinear differential problems. As you know, this event is organized in the context of the project PRIN Nonlinear Differential Problems via Variational Topological and Set-Word Methods, supported by the Ministry of Education, University and Research of Italy. In this session, the distinguished lecture will be delivered by Professor Kanishka Perera, followed by the short talk given by Elisa Assani. On the behalf of the organizer, I wish to thank the speaker for accepting our invitation. So many thanks to Professor Perera and many thanks also to Dr. Assani. Thank you very much also to the audience for your participation.
Scusi, io devo
Before we start
un impegno.
with the first talk, as usual in this webinar, I would like to spend some few words to sketch the scientific profile of Professor Perera. Professor Perera takes the PhD in mathematics at the Courant Institute of New York in 1996, and from 2007 is a full professor at the Florida Institute of Technology. The mathematical skill of Professor Perera cover many topics concerning variational and topological methods, useful to study nonlinear partial differential equation. Among the other, I recall that he is one of the main experts in the study of non-compact variational problems, as for instance, variational problems with nonlinearities involving critical growth or defined on unbounded domain. Moreover, in his research activity, he studies singular Truding-Moser nonlinearity and different type of operator, as the classical P-Laplacian and the more recent Kirchhoff type of operator, or the more recent fractional P-Laplacian. Professor Perera is really very good, as you can see in the talk. Is very good to combine the classical result on critical point theory with various notions of linking and with some power tools arising from algebraic topology, and in particular homology theory, to study critical groups associated to isolated critical points. You can find a detailed introduction on these topics in his book, for instance, book written in collaboration with Martin Schechter and published of Cambridge University Press. Finally, let me say that for me and the other organizer, as well as for all the participants in the PRIN project, it is a great honor and very proud, and we are very proud to have a long collaboration with an high-level mathematician and a very kind person as Professor Perera. Dear Kanishka, thank you very much for your collaboration and friendship. The talk this afternoon, Professor Perera will speak about an abstract critical point theorem with application to elliptic problems with combined nonlinearities. Please, Kanishka.
Thank you, Pasquale, for the kind introduction. And I would also like to thank the organizers for their kind invitation for me to give this talk today. So let me share the screen. Okay. Okay, so so let me start with with an application that motivates this talk. So here's the model problem with combined nonlinearities that we are going to talk about. So delta p is the p Laplacian, and then you have a term that's of the order p minus 1, and then you also have two terms, one of which is of order less than p minus 1, the other one is of order higher than p minus 1. So this sigma is between, I'm sorry, so p is between sigma and q, and we are looking at the problem in a bounded domain in Rn, n is bigger than or equal to 1, and q can be up to the critical exponent p star if p is less than n, and no restrictions on q if p is bigger than or equal to n. And lambda mu are both positive parameters. So the idea is to look for two critical points, two non-trivial solutions of problems of this type that have combined nonlinearities in this sense. So basically I will present a new abstract critical point theorem that will give you pairs of non-trivial critical points that you can then apply to problems of this type with combined nonlinearities. So let me first give some background information about the history of this problems of this type. So first of all, if you denote by lambda 1 the first directly eigenvalue of the negative p Laplacian on omega, the case where lambda is between 0 and lambda 1 and mu is small can be treated using the subband supersolution method and the mountain pass theorem. So this is an argument that goes back to Ambrosetti, Brazis, and Cerami in 1994. So they considered a problem of this type with, but in the semilinear case, p equal to 2, and they took lambda to be 0. So basically you have the equation negative Laplacian of u equals the sum of the last two terms of this equation, and they showed that you can construct a positive subsolution and a positive supersolution that are ordered, and so you can now look for a solution between the sub and the supersolutions. And so that's basically a local minimization argument. So you can so the solution you get from the sub and supersolution method is basically a local minimizer of the associated variation of functional. And once you have a local minimizer, the function is also unbounded from below, so you can look for a mountain pass point. So using this argument, they show that this problem has two positive solutions if lambda is equal to 0 and p is equal to 2. And then later other people extended this result to the p Laplacian. So here I have given some references. Of course, these are not all the references. These are just a sample. So for the case if where p is different from 2, you can still use the method of Ambrosetti, Brazis, and Cerami if lambda is less than lambda 1. So the functional will still have the mountain pass geometry, and then you can look for a local minimizer and a mountain pass point. So the talk is mainly about the case where lambda is bigger than lambda 1, And in that case, the variational functional does not have the mountain pass geometry. And as far as I know, there are no results in the literature that gives multiplicity results for problems of this type when lambda is bigger than or equal to lambda 1. So what I'm going to present is a linking theorem that's based on the cohomological index of Fadel and Rabinowitz that can capture the geometry of this functional and give you a pair of non-trivial solutions for all positive lambda, in particular for lambda bigger than or equal to lambda 1, as long as mu is small. And the critical points, the solutions that we get here are not local minimizers or mountain pass points in general. So these the solutions that we get are higher critical points in the sense that each critical point has a non-trivial higher critical group. So let me just recall the definition of critical groups. So suppose you have a C1 functional defined on a Banach space W, and you have an isolated critical point U0. So the critical groups of E at U0 basically measure the change in the topology of the sublevel sets of the functional in a neighborhood of the critical point. So if you denote by, so suppose C is the corresponding critical value. So it's a critical value for the critical point U0, and as usual, it's denoted by E super C, the sublevel set where E is less than or equal to C. And then you look at the pair of sets EC and EC with the critical point U0 removed. So you want to study the change in topology when you go from EC to EC minus U0. So one way to do this is to look at the relative cohomology groups of this pair, and the qth critical group of E at U0 is defined to be the qth cohomology group of this pair. So you have this sequence of the cohomology groups that describe the nature of the critical point U0. And for example, if U0 is a local minimizer, then the critical groups will have rank 1 in dimension q equal to 0, and will have rank 0 in all the higher dimensions. And in the case where p is equal to 2, for a mountain pass point, the critical groups will have rank 1 in dimension q equal to 1, and 0 rank in all the other dimensions. And even in the case where p is not equal to 2 for a mountain pass point, the critical groups, the critical group in dimension 1 is non-trivial. So the critical points that I'm going to construct for this functional for lambda bigger than or equal to lambda 1 have non-trivial critical groups in dimensions q greater than or equal to 2. So they are, so in some sense, first of all, they are not local minimizers at all, and in some sense, they are not mountain pass points either. You have change in the topology of the sublevel sets in dimensions higher than 1. Okay, so let me describe the critical point theorem. So here's our setting. Suppose we have a Banach space W, and you have a bounded symmetric subset not containing the origin M, and this set M is assumed to be radially homeomorphic to the unit sphere in W, meaning that if you take the restriction to M of the radial projection onto the unit sphere, that's a homeomorphism. And in applications that I'm going to present, M will actually be the unit sphere. But for the general theorem, it could be any bounded symmetric set not containing the origin and radially homeomorphic to the unit sphere. So, so this homeomorphism means that if you take this radial projection, it's and restrict it to M, it's a homeomorphism, and in that case, you can get the radial projection onto M by first taking the projection onto M. I'm sorry. You take the projection onto the unit sphere and composing it with the inverse of the restriction of the projection onto unit sphere to M. So you have this this radial projection pi M onto the set M, and then this will come in the statement of the abstract critical point theorem. Okay, so to state the theorem, let me denote by I of A the Z2 cohomological index of a symmetric subset of W minus origin. So A is a symmetric set not containing the origin, and I'm denoting by I of A its cohomological index. So here's the statement of the theorem. So suppose you have a C1 functional E on a Banach space W, and we are going to construct two sets that link on which the values of the functional are bounded away from each other. So the starting point is two sets A0 and B0 that are disjoint, closed, and symmetric subsets of M, with the property that A0 and the complement of B0 in M have the same finite cohomological index. So, to visualize this, I have drawn a picture. So in this picture, so in the first picture, suppose this round set is the set M, and suppose these two dark areas denote the set A0, and this band is the set B0. So the assumption is that A0 and the complement of B0 in M have the same index, and then we are going to construct several sets based on A0 and B0. So the next assumption is that there is some point W0 in M that's not on A0, and based on this W0, we are going to construct another set A1. So A1 is basically, so here's what you do. You take all line segments joining points in A0 to this external point W0, and you project those line segments onto the set M. So in the picture, so here's what the set A1 might look like. So we have this round set M, and then you have these two shaded areas that are A0, and then you have this other point W0 on M that's not on A0, and you take all line segments joining points in A0 to W0 and project those line segments onto M. So you get a set like this. That's your A1. And then based on this A1, we are going to construct two sets that link. So the first set, let me just go back to the picture. So here's the first set A. So how is this set constructed? Well, so you have this this front piece that's basically a scaled copy of A1, and then you also have this this rear piece that's also a scaled copy of A1. So you have two scaled copies, one in the front, one in the rear, and then you connect them. So each of these two copies will have scaled copies of A0. So here's the A0, the scaled copy of A0 on A, these two parts, and on the rear piece again you have two scaled copies of the set A0, and you take the corresponding points on those two scaled copies and connect them by line segments. So that gives you this set A, and the set B is basically a scaled copy of the set B0, and notice that the set A does not go through the origin. There's a small indentation here that that serves to avoid the origin, and this rear copy of A1 is on a sphere of radius, a small sphere, and then the set B is on another sphere of slightly larger radius, and finally this front copy of A1 is on a sphere of very large radius. So this is the picture of these linking sets, and notice that this kind of resembles the classical linking theorem of Rabinowitz, except that the linking sets are not made up of pieces from linear subspaces of W. And the reason for that is that if you want to apply this type of theorem to P-Laplacian problems, you have to realize that the P-Laplacian does not have linear eigenspaces. So it's a nonlinear operator. So if you look at the eigenvalue problem for the P-Laplacian, that's a nonlinear eigenvalue problem. So it does not have linear eigenspaces. So you cannot use linking theorems based on linear subspaces to work with the P-Laplacian. So one way to get around this problem is to construct linking sets based on the cohomological index. That gives us enough information to deal with the problems of this type. Okay, so let me finish the statement of the theorem. So we have constructed these two sets, A and B, and then denote by B star the set of all line segments joining points on B to the origin. So that will be your B star. And then we have this other set A star. So here's what A star is. So you look at these two copies of A1. So you have they're both scaled copies. So you have the front copy and the back copy. And so there are corresponding points on each because they're just scaled version of the same thing. And take the set of all line segments joining points on this rear copy to the corresponding points on the front copy. So that's kind of a thickened set. So that's basically a set that fills in the set A to get this set A star. So that is what A star is. And okay, so this is the geometry of the linking sets. So here are the assumptions on the functional E. So assume that E is the infimum of E on B star. So the infimum on E on B star is bigger than or equal to bigger than A. So meaning that E is bounded from below on B star. And this second inequality is the main assumption. So this says that the values of E on A and B are bounded away from each other. So on A, so the supremum of E on A is less than the infimum of E on B. And finally, assume that E is bounded from above on A star. So on the filled in set, the supremum of E is less than B. So those are the assumptions on E. And then we're also going to assume that there is some compactness in the problem. So assume that E satisfies the PSC condition for all C between A and B, where A is here and B is there. And then the conclusion is that E has a pair of critical points, U1 and U2, and the critical value of U1 is less than or equal to the supremum of E on A. So E of U1 will be less than or equal to the infimum of E on A. And we can also get a lower bound. It will be bigger than or equal to the infimum of E on B star. And so that's one critical point. The other, so this critical point has a critical value less than the supremum on A. The other one has a critical value that's greater than the infimum on B. So E of U2 will be greater than or equal to the infimum of E on B, and you also have the upper bound that is less than or equal to the supremum over A star. So we have these two critical points with estimates on the critical values. And if in addition, if you assume that E has only a finite number of critical points with values between A and B, then you can choose U1 and U2 in such a way that the kth critical group of E at U1 is different from 0, and the k plus first critical group of E at U2 is also different from 0. Remember that this k is the common cohomological index of A0 and M minus B0. So that k appears in the non-trivial critical groups that you get for U1 and U2. So this is the statement of the theorem, and the proof is based on properties of the cohomological index and doing a lot of what algebraic topologists call diagram chasing. So you have lots of commutative diagrams for these sets, and you show that you can get certain pairs of sublevel sets with non-trivial relative cohomology. And the main step is actually a new linking result. So let me first recall the definition of cohomological linking, because the proof is based on this definition. So suppose you have two disjoint non-empty subsets of a Banach space W. We say that the set A links the set B cohomologically in dimension k if the inclusion of A in W minus B gives rise to a non-trivial homomorphism of the corresponding reduced cohomology groups in dimension k. So A and B are disjoint. So A is contained in the complement of B. So you have this inclusion of A in W minus B. So so that induces a homomorphism on the reduced cohomology groups going in the opposite direction in all dimensions. And if this homomorphism is non-trivial in dimension k, then we say that the set A links B. And here's the main step in the proof of the theorem. The main step is that if you have two sets A0, B0, as in the theorem, with a common cohomological index for A0 and the complement of B0 in M, then the set A links B in cohomologically in dimension k. So this is the main step in the proof of the theorem. So you basically show that if A0 and the complement of B0 have index k, then the set A links this set B cohomologically in dimension k. And once you prove this, you can use that to try and find pairs of sublevel sets with non-trivial relative cohomology in dimensions k and k plus 1, and that's basically what gives you these two critical points U1 and U2. Okay, so now let me give the main multiplicity result in an abstract setting. So basically we want to apply this to P-Laplacian type problems, but you can apply this not just to P-Laplacian type problems, but many other problems that have the same structure. For example, you could apply this to Kirchhoff problems, non-local problems. You could also apply to P-Laplacian problems, fractional P-Laplacian problems. So let me state an abstract multiplicity result. So we are going to do this in an abstract operator setting. So suppose you have a uniformly convex Banach space W with dual W star. So let me recall that an operator H from W to W star is called a potential operator if it's the Frechet derivative of a C1 functional capital H on W. So little h is a potential operator if it's equal to capital H prime for some C1 functional capital H on W. So with that, here's the operator setting. So consider this nonlinear operator equation. You have APU plus lambda BPU equals mu FU plus GU. So in the example that we looked at the beginning, this APU will be the negative P-Laplacian. This BPU will be just u to the power p minus 1, and f is u to the power sigma minus 1, and g is u to the power q minus 1. Okay, so these operators AP, BP, F, and G are continuous from W into its dual, and they are assumed to be potential operators, satisfying a list of assumptions, and I will state the assumptions on each operator. And lambda and mu are positive parameters. So AP is assumed to be p minus 1 homogeneous and odd for some p between 1 and infinity. So this means that AP of TU is t to the power p minus 1 with the appropriate sign times APU for all u and t. And then we have a boundedness condition on AP So the condition is this Holder type inequality that should hold for all u and v, with equality if and only if u and v are non-negative multiples of each other. So in particular, if u and v are the same, you have equality. So APU is the norm of u to the p. So again, the P Laplacian satisfies all these assumptions. So does the fractional P Laplacian, and so on. And then BP. So here are the assumptions on BP. So BP is the second term. It's basically something that generalizes the u to the p minus first power. So this is also assumed to be p minus 1 homogeneous and odd, and it's assumed to be positive. BPUU is assumed to be positive if u is different from 0. Again, u to the power p minus 1 in the usual P Laplacian equation satisfies this. And we also have this Holder type inequality assumed on BP. Again, this is just the Holder inequality in the model example. And finally, BP is assumed to be a compact operator. Okay. And so here are the assumptions on the operator f. So f is something that generalizes u to the power sigma minus 1 with sigma less than p. So denote by capital F the potential of little f with f of 0 equal to 0. So you can always assume that the potential is 0 at 0 by just subtracting f of 0. Because if capital F is a potential, then f minus any constant is also a potential. So capital F basically has to be something like a power sigma, where sigma is less than p. So the main assumption is that if you divide f of tu by mod t to the p, that goes to infinity when t goes to 0, and the limit should hold uniformly on compact subsets of w minus 0. And it's also, and the potential is also assumed to be positive except at the origin. And finally, it's assumed to be bounded on bounded subsets of w. And all of these things are satisfied in the model example, where capital F is basically something like a u to the power sigma. And finally, here are the assumptions on G. So G is basically the p superlinear power, something like u to the q minus 1 with q greater than p. And so the potential capital G with G0 equal to 0 should go to 0 when divided by the norm of u to the p. So that's the main assumption on G. Capital G of u is little o of norm u to the p as u goes to 0. And G is also assumed to be positive except at the origin. And G is also assumed to be bounded on bounded subsets. And finally, this should be a p superlinear term. So we assume that G of tu divided by t to the p goes to positive infinity as t goes to positive infinity uniformly on compact subsets of w minus 0. So this is the abstract operator setting. So you could think of this as an abstract P Laplacian problem with combined nonlinearities. And so this problem has a variational formulation because all the operators are potential operators, so you can put together their potentials to get the variational functional. So the solutions of this equation coincide with this C1 functional on W, the potential of capital AP is 1 over P norm u to the P. For BP, it's 1 over P BP U, and then you have the potentials for F and G. So the theorem is that if you assume A1 through G4 and that E satisfies the PS condition, then for each each lambda positive, there is a mu zero such that this equation has two non-trivial solutions, U1 and U2, with U1 with negative energy and U2 with positive energy, if mu is between 0 and mu 0. So regardless of what lambda is, for small enough mu, you always get two non-trivial solutions, one with positive energy and one with negative energy. How much time do I have?
10 minutes.
10
10 minutes. Okay, more or less.
Okay, 10 minutes. Okay. So without going into a lot of details, let me just indicate how the abstract critical point theorem is applied to prove this multiplicity result. So it involves this nonlinear eigenvalue problem for the operator AP. So you can look for eigenvalues of this problem by looking for critical points of this functional psi u, which is basically 1 over the potential of BP, restricted to the manifold. Basically here this is a sphere, or basically it's a sphere of radius p to the power 1 over p in W. If you and one can show that the critical values and critical points of psi correspond to on M correspond to the eigenvalues and the eigenfunctions of this eigenvalue problem. So now you can define a sequence of eigenvalues based on the cohomological index. So suppose capital F is the class of symmetric subsets of M, again denoted by I of M, the cohomological index of a set M, and you do minimax on this class of sets. So suppose Fk is a set of symmetric subsets of M with index greater than or equal to k, and then you set lambda k to be the infimum over M in Fk with supremum of U in M of psi u, with the usual minimax scheme for defining a sequence of eigenvalues, but the usual one uses the Krasnoselskis genus rather than the cohomological index. But if you go that route, we don't get enough information about the lambda case to apply this multiplicity result, the abstract critical point theorem. So you have to use the cohomological index instead of the genus to define your sequence of eigenvalues. So you get an increasing and unbounded sequence of eigenvalues. And by the way, the eigenvalues based on the cohomological index was first introduced in this paper in 2003 in topological methods in nonlinear analysis. Okay, so and then if you denote by psi super A the sublevel sets, sublevel set of where psi is less than or equal to A, and psi sub A, the superlevel set where psi is bigger than or equal to A, we get the following information about the sublevel indexes of the sublevel sets of psi. So if lambda k is less than lambda k plus 1, the sublevel set where psi is less than or equal to lambda k, and the superlevel set where psi is greater than lambda k plus 1 both have index k. And then but this itself is not enough to apply the abstract critical point theorem. So one of the main steps in the proof is this lemma. You show that if lambda k is less than lambda k plus 1, then the sublevel set psi lambda k has a compact symmetric subset A0 of index k. So once you have that, basically what you do to apply the abstract critical point theorem is look at the two cases where lambda is between 0 and lambda 1 and lambda bigger than or equal to lambda 1. In the first case, take your set A0 to be empty, B0 to be the whole set M. So both A0 and the complement of B0 have index 0. And if lambda is bigger than or equal to lambda 1, then it will satisfy two inequalities like this for some k bigger than or equal to 1. So lambda will be greater than or equal to lambda k and less than lambda k plus 1 for some k. And then you take A0 as in the last lemma. The A0 is the compact set of index k constructed in the last lemma, and you take the set B0 to be the superlevel set where psi is lambda greater than or equal to lambda k plus 1. Then A0 has index k, and by this second equality here, the index of the complement of M is a complement of B0 is also k, and then now we can apply the critical point theorem. So do I still have a couple of minutes?
Yes, yes.
Okay, so let me just describe the application to the P-Laplacian problem. So consider this, first consider this subcritical P-Laplacian problem. It's the same one that you looked at earlier, but you can have, I put a more general term, f that sort of looks like u to the sigma minus 2u. But if you take u to the sigma minus 2u, then the problem has odd symmetry, so you can get solutions in other methods. So let me get rid of that by just introducing a more general term f that's not assumed to be odd in u. So you cannot use index theories to get multiple solutions. And so this is a p-linear term, this is the p sublinear term, and the p superlinear term, and the result is that if the superlinear term is it grows slower than the critical exponent, then you can find two non-trivial solutions, one with negative energy and one with positive energy, if mu is small enough, with no restrictions on lambda. So lambda could be bigger than or equal to lambda 1. And you just apply the abstract multiplicity result with these choices for the operators AP, BP, F, and G. And you can easily check that all the assumptions on the operators hold here. And by the way, the semilinear case where P is equal to 2 of this theorem was recently proved in a paper with Candito and Marano to appear in Communications in Contemporary Mathematics. But there we were in a linear setting, so we were working with the Laplacian rather than the P-Laplacian, so the eigenvalue problem is linear. So you could so you have linear eigenspaces, so you could construct linking sets in a more standard way without using the cohomological index. Okay, since I don't have time, let me skip this example to a Kirchhoff problem and go to the critical case. Okay, so there's a variant of the abstract multiplicity result that you can also apply to critical problems. So assume that the functional, instead of satisfying the PSA condition for all C, only satisfies it for C less than some C mu. So you need an additional assumption in that case. The additional assumption is that if lambda is less than lambda 1, assume that there is some W0 on the set M, such that on the line or on the ray starting from the origin and going through W0, the sup of E is smaller than C mu. And if lambda is between lambda k and lambda k plus 1, assume that there is a compact symmetric subset C of psi lambda with index k and a point W0 in the complement of C in M, such that if you take the sup of E of SV plus TW0 with V in C and S and T non-negative, that's smaller than the C mu, then you get the same conclusion as in the other theorems, namely that for any lambda you can find a small enough mu0 such that if mu is between 0 and mu0, you get two critical points, one with negative energy, one with positive energy. The one with the positive energy will have energy less than the C mu, the threshold for compactness. And then here's a quick example of this for a critical field Laplacian problem. So suppose the P superlinear term is critical, and same assumptions hold for F. And denote by sigma of negative delta P the Dirichlet spectrum of the P Laplacian. So this is a set of all eigenvalues of this eigenvalue problem, and let S be the best suborder constant. Then the result is that if P is bigger than 1 and n is bigger than or equal to P squared, and lambda is not in the spectrum, then you can find two small numbers mu0 and kappa, such that the problem has two non-trivial solutions for mu between 0 and mu0, and their energies will satisfy these inequalities. So the energy of the one with positive energy will be less than this. Basically, this is a threshold for compactness in this problem. And again, the semilinear case P equals 2 of this theorem was proved in the paper with Candido and Marano that I mentioned. Okay, I'm out of time, but you could also do the same thing for fractional P Laplacian problems. So here's the same equation for the fractional P Laplacian. So we have this fractional critical exponent, and okay, I'm going to skip all the details. And the result is that if P is bigger than 1 and n is bigger than SP squared, and lambda is not in the spectrum, then again you can get two non-trivial solutions, and this is the threshold for compactness in that case. Okay, so I guess I'm out of time. So thank you for your attention.
Thank you very much, Kanishka, for your very interesting talk.
Thank you.
There are questions?
Pasquale, there is Umberto Guarnotta.
Okay, Umberto, please.
And
thank you. I was wondering about the possibility to find a third solution via Morse theory. Is it possible with some additional conditions to get another solution?
Well, the difficulty here is that to apply something like Morse inequalities, you need to know all the critical groups of the critical points U1 and U2, but we don't have information about all the critical groups. All we know is that in certain dimensions, they have non-trivial critical groups, and we don't know what happens in other dimensions. So that's a difficulty. But on the other hand, if you can also prove that the functional has a local minimizer, you can distinguish that from the two critical points that you already have, because if k is bigger than or equal to 1, then both k and k plus 1 will be bigger than or equal to 1. So if critical groups are non-trivial in dimensions k and k plus 1, U1 and U2 cannot be local minimizers. So if you can find a local minimizer, you can conclude that that's a third solution. So that's one way to maybe do that.
Okay, okay, thank you.
Sure.
There are other questions? Kanishka, just on curiosity. So
Yeah.
for the energy functional, the abstract energy functional, there are no results which ensure the existence of a local minima for that energy functional.
Not that I know of.
Okay.
But I mean, of course, if lambda is less than lambda 1, yeah, you do. You have a
Okay.
local minimizer and
No, for lambda bigger than lambda 1.
no, I don't know.
No.
No.
Okay. Thank you.
Sure.
There are some other remarks? If not, thanks again to Kanishka.
Thank you.
And
Thank you.
now we have